So in this video, we're going to be talking about two-level systems. And this is going to be the first step in deriving Fermi's golden rule, which will allow us to analyze semiconductors in their entirety. So first of all, what is a two-level system and why should you care? Well, a two-level system is just saying we've got some system or two different states. One has energy E1 and the other has energy E2. And so if you've taken semiconductor physics, which I'm fairly confident you have at this point, you know that we've got conduction bands and valence bands. And inside those bands, there's a huge number of very closely spaced energy states. Well, we're just picking one of those states and calling that E2. And similarly, we're picking one of the states in the valence band and calling that E1. And the reason we're analyzing a two-level system instead of two bands is because it's way simpler. And all we'll need to do in the end is perform a sum over all possible states or an integral. And so that's all we're going to need to do to extend this two-level system into as many levels as we want. So we're ultimately curious about how light interacts with matter. So if we've got a chunk of semiconductor and we irradiate it with some light, we want to know what happens. And so similarly, we want to know what happens when we irradiate our two-level system with light. And let's say for now that, for example, we've got an electron in state E1. So we want to know what happens when we've got an incoming light of some frequency or equivalently some electric field strength. And so we might kind of intuitively understand, well, we expect this semiconductor to absorb some of the incoming photons, depending on their frequency. And so we kind of expect this electron to transition from this low energy state to this high energy state. And in this video, we're going to be actually using Schrodinger's equation to derive exactly what happens in this situation. And so how do we model this? So how do we model this system? Well, the answer is we're going to use quantum mechanics, and in particular, we're going to use Schrodinger's equation. So Schrodinger's full equation, we know we can write as IH bar d psi, and this is capital psi, so this is a function of space and time, and I'm just going to write that as x for now. This is equal to our Hamiltonian times psi, which is a function of x and t. And so we'd like to know what psi is for this two-level system, or let's call it psi total. So let's put a subscript t there. And unfortunately, this two-level system, we know it's existing in sort of a crystal lattice, so inside the semiconductor. And so in general, the wave functions, let's call this the wave function psi1 for energy 1. And for energy 2, we've got similarly some other wave function, psi2 of x and t. They're actually going to be really complicated, as is this Hamiltonian, because this Hamiltonian contains the potential term, which essentially accounts for all of these atoms inside the silicon. And so the Hamiltonian and the wave function are hopelessly complicated, or maybe not hopelessly, but we don't want to deal with that complexity right now. So we're just going to say, well, psi2 is this and psi1 is this, and we're going to leave it at that. And so we're going to try as much as we can to simplify this equation, so to simplify the Schrodinger equation using what we know without ever assuming a value for psi or even the Hamiltonian. So initially, this two-level system, since we know we have an electron in the state E1, we can write that psi total of x and t is just equal to psi1 of x and t. So that's physically how this system is initially modeled. And so let's call that psi of x 0. So psi of x 0 is just psi1 of x at time 0. But we're interested in what happens at time t. So we're interested in what happens when you add this light into the system. And so we know we're probably going to still have some, eventually we're expecting that our wave function will become just psi2 of x and t. So eventually, or let's call this x and infinity. So after a very long time, we're expecting a photon to get absorbed, and we're expecting the wave function to become psi2, which would just correspond to an electron in this energy state E2. So it's no longer in energy state E1. But we're actually interested in what happens in between. So kind of what happens as the electron is making its transition from state 1 to state 2. And so in general, this total wave function is actually going to be a combination. So some unknown combination of psi1 and psi2. And so these C1 and C2 coefficients are, we don't know what they are. We'd like to figure out what they are. So C1 is equal to what, and C2 is equal to what. We know that they're functions of time, though, because initially we know that C1 has to be 1 and C2 has to be 0. So initially, C1 at time 0 equals 1, and C2 at time 0 is equal to 0. And this just means the electron is in state 1, or has energy 1. Is in state 1. But we know that eventually it's going to be, as the photon get absorbed, C1 at some very long time should be equal to 0, and C2, C2 at some very long time, let's say infinity. Let me just erase this. C2 at some very long time, infinity, should be equal to 1. And we want to know, ultimately, C1 as a function of time, and C2 as a function of time. So I'm just going to write that time dependence explicitly back in this equation. So C1 as a function of time, and C2 as a function of time. And so this is our known solution to this two-level system. And so now we just want to plug this back into the Schrodinger equation and hope that we can figure out what C1 and C2 are as a function of time. And the fact that we can do this, and we can actually do this without knowing what the wave functions are, is actually pretty cool. But before we plug it in, let's say one last thing. Let's make one last simplification. We know from previous videos that we can write psi1 if it's an energy eigenstate or has some well-defined energy, which it does. We said that it has some energy E1. We know that it can be written as some wave function, which is just a function of space, times e to the minus I omega 1 t, where omega 1 was just defined as the energy of that state over Planck's constant. And similarly, we can write psi2 as a function of x and t, and these are the separate states for energy E1 and E2. Wave function 2 as a function of x times e to the minus I omega 2t, and omega 2 is defined similarly just to be E2 over h bar. And initially, let's just assume that there's actually no light. So let's figure out what happens when there's no light being applied to the system. So this Hamiltonian is just a function of x. So h is just a function of x. And so at this point, I'd recommend you try plugging in this full equation using these substitutions into the Schrodinger equation. You're going to need to use probably the product rule here, because you've got two functions of time multiplied by each other, as well as here. And the equation you get is going to contain quite a few terms, and I'll write it down in just a moment. And so try and take some time to do that substitution yourself. Once you do, you should get something that looks like this. So IH bar dc1 dt, and I'm just going to drop the time dependence. So C1 and C2 are functions of time, psi1 and psi2 are functions of x, and the Hamiltonian is also a function of x. But for my own sanity, I'm going to avoid writing all those dependences down in the below text. So e to the minus I omega 1 t plus h bar omega 1 c1 c1 e to the minus I omega 1 t times psi 1 plus the two terms that are basically identical that have to do with c2 e to the minus I omega 2t. Oh, and sorry, this should also have a psi 1. Psi 2 plus h bar omega 2 c2 e to the minus I omega 2t times psi 2. Woo! And this is our entire left-hand side of the function. So this is what happens when you differentiate the total wave function with respect to time. And this is all equal to, on the right-hand side, you should just get c1 times e to the minus I omega 1t times this Hamiltonian times psi 1 plus c2 e to the minus I omega 2t times the Hamiltonian times psi 2. And you might say, well, Jordan, this is hideous and disgusting. What am I supposed to do with this? But remember a couple of things. So over here, we've got this Hamiltonian acting on psi 1. And remember that this is, since this psi 1 is just a function of x, we can use the time-independent Schrodinger equation to say that this is equal to E1 times psi 1. So we can actually replace, and this is because psi 1 is an energy eigenstate. It has a defined energy. So E1 times psi 1. And similarly, we can do the same over here, E2 times psi 2. And also on this side, we've got these terms h bar omega 1 and h bar omega 2. But remember, just above, we defined omega 1 and omega 2 to be E1 and E2 over h bar. So E1 is just equal to h bar omega 1, and similarly E2 is equal to h bar omega 2. So we can replace these also with the energy, so E1 and E2. And now we can cancel some stuff. So now this term and this term cancel, and this term and this term cancel. And so we're left with our final differential equation, which is just IH bar dc1 dt e to the minus I omega 1t times psi 1 plus IH bar dc2 dt e to the minus I omega 2t times psi 2 is equal to 0. And this is going to be our starting point for the next video and for the complete derivation of Fermi's golden rule. So if you liked the video, please give it a like and subscribe to my channel. If you really liked it, consider becoming a patron of mine on Patreon. The link is in the description below. And if you have any questions or comments, please post them down below and I'll try to get back to you as quickly as possible. And I'll see you next time. Thanks for watching.